because resource planning is so vital in this industry. No other industry on the planet requires the capital investment and operating expense that electric power does. No other industry on the planet does its resource planning and capital investment in the public domain like electric power does. It's important to get resource planning right, since failed planning undermines the ability to reliably serve load and remain a viable entity in today's rapidly changing marketplace. We refer to this topic as IRP 2.0 as a convenient way to communicate that we are seeing a significant evolution in the traditional IRP planning process, which has been around almost 30 years now. As perhaps everyone in the room can attest, traditional long-term central station-based resource planning is being challenged in today's environment. The greatest driver of this is changing resource type and topology. Mandates for sustainability and decarbonization have moved renewables to the top of the planning stack. This in turn has increased the need to plan for greater energy intermittency, a more dispersed set of resources, since renewables are not constrained to central station locations, and the rise of storage and electric vehicles for greater renewable utilization and decarbonization. The result is a foundational shift in planning from dispatchable resources at the transmission level to variable resources at the distribution level. Change is also being driven from the customer end. A growing number of large customers are actively implementing renewable energy, smart energy technology, and data analytics to control and decarbonize their own loads, rather than wait for their utility provider to do so. These changes at the resource and customer level are driving increased uncertainty and risk for electric utility planners. Solar and battery storage technologies, while bankable, are still relatively unproven for long-term utility service that typically spans decades. Declining energy prices due to the proliferation of solar and natural gas are masking a tremendous increase in the value of energy availability and capacity. With real estate, value is driven by location, location, location. With power, value is becoming more driven by timing, timing, timing. Finally, the success of energy efficiency and the threat of retail choice has led to declining load growth and reduced profitability for utilities, with revenues still tied primarily to investment rather than service. This increases retail rate impacts and decreases the set of economically viable resource portfolios to be considered. We're finding that utilities need solutions to adapt planning to this changing environment. So what do we believe these solutions look like? To deal with changing resource type and topology, we're seeing three types of solutions needed. First, improved integration of generation, transmission, and distribution planning. There needs to be closer interaction of planners across the entire electricity supply chain to understand how decisions at one planning level may impact other levels, as well as the ability to make trade-offs between potential investments in each of these subsystems to optimize the future overall electric power system. Second, increase modeling precision for the distribution system. Models for conducting long-range resource planning need to include finer geographic resolution and temporal granularity on the distribution system, since distribution resources are becoming a larger component of the resource base and therefore must face the same rigorous modeling and evaluation as larger central station resources. Finally, incorporation of system operation analysis into the planning process. As new renewable resources replace new synchronous generators in the stack, resource planning must explicitly consider the operating reliability capabilities of the new resources and the remaining resources to ensure overall system operating reliability. This includes consideration of startup and ramp rates, minimum load levels, and VAR support available from advanced inverters. To deal with changing customer preferences, we see a need for improved load forecasting. The typical load forecasting methodology, analyzing broad economic trends, customer class data, and weather, is becoming less accurate as customers adopt self-generation, demand response, smart energy, electric vehicles, and storage to decarbonize and manage their own loads. Planners need improved forecasting tools that consider customer behavior and the response to incentives, and more precise geographic mapping of customer loads and load types so as to more accurately forecast loads net of customer energy supply, storage, and demand resources. We also see a need for better integration of procurement into the planning process. Planners need more accurate and timely information. Timely information from the marketplace on the energy capacity or ancillary services that developers, aggregators, and customers will be offering to the utility. procurement function, long subservient to planning, must become more integrated with the planning process to provide advanced information to planners and more customized information to proposers on the type, size, and location of desired resources. With respect to increased uncertainty and risk, as renewable energy assumes a greater presence in the stack, the influence of weather and other conditions on system energy availability and capacity becomes elevated. Similarly, increased liquefaction and export of natural gas will result in greater volatility in gas prices. Planners need tools to allow stochastic analysis of weather variability and gas price variability on the overall energy availability, capacity, and cost of the resource portfolio. Finally, implementation of the aforementioned solutions will add duration to the typical resource planning cycle as planning becomes more comprehensive and precise. To compensate, planners need more powerful solution, simulation, and data analytics software to shorten analysis times and ensure agile response to the real-time information demands of regulators, customers, and stakeholders. Stepping back and reviewing these needs together, it's apparent that planning must be made more comprehensive, more precise, and faster to adapt to the challenges of new energy. Let's drill down into some of these solutions, starting with improved integration of planning processes. Here's a schematic showing today's typical process for a vertically integrated utility delivering both electric and gas service. The typical process involves development of multiple future scenarios of electric load demand, fuel prices, RPS requirements, and carbon reduction goals that are modeled to generate a resource and investment and procurement plan. There's coordination with the transmission planning process to identify the transmission build necessary to accommodate each scenario. There is, however, limited coordination with the distribution planning process. This is typically done annually based on area level forecasts of load growth. There is typically little or no coordination with the gas system planning process, which is done on an annual basis using local load and overall maximum cold day demand forecasts. So we have multiple separate processes with limited integration, differing cadence, distribution planning focused on wires, and gas planning not integrated. We're seeing that the trend towards maximum renewables and deep decarbonization requires much greater integration of these disparate processes. Planning, but also to distribution and gas system planning, since these systems will play a large role in the future electric resource build-out. The processes should move to a common cadence if possible to support the use of common scenarios and assumptions. The distribution planning process should be expanded to consider the same factors that impact central station planning: hosting capacity, interconnection commitments, resource cost and value, and the current and future programs that will pull DER resources into the marketplace. Procurement should be integrated into each of these planning processes, since customers, aggregators, and developers will play a larger role in the build-out or avoidance of future resources and transmission. And advanced knowledge of their plans and capabilities will be necessary for good planning. Gas system planning should be expanded to consider electrification of building and industrial process loads and the availability of renewable gas as a resource. And the investment decisions for each system should be based on a comprehensive optimization across all the systems, so that trade-offs between potential investments can be understood and the investments made as a group to help achieve renewable and decarbonization goals. With respect to increased distribution system modeling precision, as DER adoption grows, we see a growing need for more state estimation modeling of the distribution system due to increasing two-way power flows. State estimation involves leveraging data available from new advanced metering infrastructure, grid sensors, field communications, smart inverters, and other devices to develop a more accurate model of the distribution system for the purposes of planning as well as real-time control. Distribution System State Estimation Modeling, or DSEE, should be as robust as Power System State Estimation, or PSEE modeling, used for the transmission grid to assess performance of both planning and resource scenarios, and therefore determination of the optimal sizes and locations of DER on the distribution grid to support system reliability and performance. With respect to system operating reliability analysis, we see that the resource planning must consider extreme loads and energy production conditions. Typical resource planning deals with average hourly loads and average energy production forecasts. However, extreme combinations of load and energy production should be examined as a part of planning, particularly if intermittent renewable resources and variable vehicle charging loads are to be added to the system. Some extreme events may have to be examined on a sub-hourly or even sub-second basis, depending upon the criticality of loads. The identification of the extreme events will require collaboration with system operating staff who know the strengths and weaknesses of the current system, including the constraints of existing resources to start up, shut down, operate at min load, and ramp to provide adequate reserves during the extreme events. Planners should also consider future conditions, such as movement of the net peak to post-sunset hours, requiring a rapid ramp-up of non-solar resource output, or the sunset ramp, as I like to call it, including the potential for commuters plugging in their electric vehicles after arriving home, which would exacerbate the problem. Similarly, transmission planning studies should be expanded to examine system dynamic disturbance ride-through and dynamic transient stability under high renewable energy production conditions. As renewable resources are added to the system, conventional synchronous generators will operate at low loads or be shut down to accommodate renewable energy production. This could result in system instability if an outage were to occur and there's inadequate system inertia. To mitigate both operating reserve and transient stability violations, it may be necessary in the scenarios to constrain gas and hydro generators to operate at min loads when typical hourly modeling would call for their shutdown to accommodate renewable energy production. With respect to improved load forecasting, we see the solution as being a shift to a more customer-focused bottom-up methodology leveraging new AMI data and customer behavior modeling. Given that customer load growth in the future will be driven by the supplier and DER technology choices they make, customers within each class, industrial, commercial, residential, should be further segmented by the structural, demographic, and financial factors affecting their propensity to evaluate and purchase new technologies. This will require modeling competitive behavior or discrete choices that the customer will face among competing products and services, similar to what sales forecasters do in the telecom, financial services, and retail industries. In parallel, AMI SCADA data analytics should allow utilities to isolate data for customers who participate in various energy efficiency and demand response programs to understand the effects of those programs on consumption and the underlying load shapes at the building level. Results from the propensity and load shape analyses can then be utilized to prepare customer segment and technology-specific load profiles, which can be rolled up to system-level load forecasts. The addition of geolocation information to each profile allows for the forecast to be presented in a detailed spatial context, providing the bottom-up neighborhood and circuit-level load shape and growth information needed for advanced distribution planning. With respect to integrating procurement, we envision a solution where today's separate and serial planning and procurement processes are replaced with an integrated two-step interactive process between the utility, developers, aggregators, and customers to identify, plan for, and procure resources customized to the utility's need. Under this process, a request for information would first be issued to the marketplace for both resources and grid services that the utility expects are needed based on its most recent resource planning and procurement. Developers, aggregators, and customers respond with their qualifications and non-binding planning level data concerning their proposed projects and products, sufficient for the utility to down-select types of resources, services, and locations for preliminary modeling in their integrated resource planning processes. High-level planning results are then shared with the market without compromising the confidentiality of the down-selected RFI respondents so that the market can refine its planned projects and products. A formal RFP is then issued with proposals binding on the respondents with the highest-ranked proposals selected for procurement. Now, this approach involves more interaction between the utility and the expanding marketplace, leading to more accurate planning of resources and grid services, and proposals that are more customized to the utility's need and therefore more valuable. Although this approach would require greater sharing of information between the utility and the market and could raise conflict and competitive concerns, we feel the benefit of more rapid identification of highly relevant and valuable resources is significant. In addition to this new approach for larger aggregated resources and services, we see customer-sponsored DER still being sourced through utility-sponsored programs and devices, much as it is today. Now, as I mentioned before, many of you may be dealing with these new needs and already changing your processes and tools. We're actively working with some utilities on implementing these changes. One example of a utility undergoing significant change is Hawaiian Electric, or HECO. Details of their efforts are available in the public domain, so we can talk about them here today. In many ways, Hawaii is perhaps one of the most difficult power planning environments, with the service territory spread across 5 islands, limited land availability, 100% renewable energy goal, and a very active customer and stakeholder base. HECO can no longer rely on the traditional central station integrated planning approach. HECO has embarked on a multi-year initiative to move from their traditional integrated planning approach to a new grid-focused integrated grid planning, or IGP, process. Here's a schematic from HECO illustrating their overall IGP process. IGP involves many of the changes we've discussed here today, including the use of a common set of forecasts and other planning assumptions for the resource transmission and distribution planning, a customer-based bottom-up load forecasting, and integration of procurement into planning. It also involves development of expanded tools for more detailed modeling of the distribution system and for optimization of the investment decisions across the grid resources, grid services, and non-wire alternatives. HECO has established several stakeholder working groups and a technical advisory panel to help develop the necessary solutions. Forecasts and planning inputs are currently under development, with the inaugural 18-month integrated process scheduled to begin in early 2020. HECO has explicitly stated its need to harmonize resource transmission and distribution planning and evaluate both traditional supply side and non-traditional DER and non-wire solutions, and develop an optimized portfolio of those solutions. HECO has self-described this effort as blowing up their traditional planning in favor of this new IGP process. No doubt the results of this effort, both successes and failures, will help the shape of efforts for other utilities with similar challenges, making the transition to IRP 2.0. And who might those utilities be? Here is a list of U.S. utilities that prepare integrated resource plans on a regular basis. As you can see, the list is extensive, with the service areas covering nearly all of the states. This list does not yet include some of the utilities that have most recently adopted integrated resource planning, such as in California, where the CPUC has taken the lead in coordinating the planning and filing of plans for its jurisdictional utilities and community choice aggregators. Each of these utilities will have a different level of need for the various solutions. Many of the larger utilities, such as Duke or Energy, may be exploring or implementing solutions consistent with IRP 2.0. The smaller utilities or those providing energy only, such as the CCAs in California, will likely have lesser needs. In any case, the demand for IRP 2.0 solutions will be growing as the key drivers of changing resource type and topology, changing customer preferences, and increased uncertainty and risk start propagating across the industry. So that concludes my presentation. As I mentioned in the beginning, this is our take on the changes impacting integrated resource planning today. I look forward to hearing your take on all of this, the key drivers, needs, and solutions. Ultimately, our goal is to provide the customized solutions necessary to ensure your success. So, thank you very much.
Okay. My app is not refreshing, so I don't see any questions on the app. So are there any from the audience that we'd like to ask Paul? I did want to ask just a little bit on the transmission distribution piece, if you just have any other recommendations on how to get those groups that traditionally are more siloed, how they coordinate a little bit better.
Yeah, that's the big question.
That's the big question.
I think, obviously the systems are different, the models are different, the cadence and the reliability needs are different. I think it's really going to be driven by the expansion of DER and the the need for customer-focused planning more than, I would say, efficiency within the process of the utility. I mean, obviously there's efficiencies to pick up with the integrated planning, but I think it's going to be somewhat driven by outside forces to the extent that there are programs that are successful and you get more DER, you're going to have more customer demands. And what you're going to end up having is DER or distributed planning kind of leading the integrated resource planning process. I could see that happening. But how we get there, it's a tough question. It's going to be very different for every utility.
All right, let's give Paul a round of applause. Thank you, Paul.
Thank you.